All right, so I'm going to talk about the time response of underdamped second order systems. So in the last lecture, we talked about the general representation of underdamped second order systems in general, and then we classify the second order systems into undamped, overdamped, underdamped, or critically damped. So today I'm actually going to talk about the underdamped second order systems. And the reason why this class of systems are of interest is that these systems not only can be found, or the time response of the system not only can be found in terms of zeta and omega n that we define, uh, but so it turns out that there are more time domain specifications that are related to second order systems, or in general underdamped second order systems, that can be also classified in terms of omega n and zeta. So the first thing I'm going to talk about today is to define what is called transient specification, and these are the specifications that are associated with underdamped responses, or the time response of second order underdamped systems. Then I'm going to relate this specification with the location of the poles of second order systems. And finally, I'm going to tie the location of the poles and the form of the underdamped second order response. And so these are actually going to be the few topics that we're going to cover today. So here you see the step response of second order systems. So if you recall from previous lecture, we characterized the transfer function of second order systems in general as g of s equal to omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared. And we call omega n natural frequency and zeta damping ratio. So now if the input to the system is just a step function u of t, the response we call it u of t, then the Laplace transform of the response y of s is going to be g of s multiplied by the Laplace transform of the input, which is u of s. And if your input is step function, then your u of s is just going to be 1 over s. And therefore, g of s multiplied by 1 over s is going to be what you see here. So now, in order to find out what is the time response, meaning what is the response in time domain, what is the step response in time domain, what you have to do is to, if you go here, so on g of s, on y of s, you would have to apply partial fraction expansion. So it would be eventually written in the form of something like this: a over s, or a1 over s, plus b1s, or rather a2s, plus a3 divided by s squared plus 2 zeta omega n s plus omega n squared. So then what you have to do is to find a1, a2, and a3 using what we call the residue test. Basically what we learned in I think the very first lecture. And if you do that, then you find the inverse Laplace transform after you apply the partial fraction expansion. Then you find the inverse Laplace transform and gives you y of t, which is step response. So without going through all the details, it turns out that the step response when zeta, which is your damping ratio, is between 0 and 1, which is actually the case for underdamped systems. So for underdamped system, the step response is going to be what you see here. So now essentially this just tells you that this is going to be your step response, right? So now the step response that you see here, so it has actually a few important terms. So one is zeta omega n, the other one is omega d. So omega d is actually defined as omega n square root of 1 minus zeta squared, so it's called damped natural frequency, because now as you see in the response, in the step response, the sine and cosine terms that are involved here, the frequency associated with them, or rather the natural frequency is actually going to be omega d. It's not omega n anymore. And the reason for that is that even the natural frequency is going to change because of the damping. Okay, so these sine and cosine functions are actually multiplied by the exponential term. So that just tells you that eventually, although cosine and sine are oscillatory terms or oscillatory functions, but since they are multiplied by this exponential function, the response eventually is going to die out and eventually going to converge to a constant. So in this case, if you let t goes to infinity, then the exponential term eventually is going to go to 0, and therefore the response y of t is going to converge to just this 1. Okay. So now the plot that you see here, that actually represents a step response as a function of not t but omega nt. So this is really a way of like normalizing the step response instead of showing it in terms of t, just showing it in terms of omega nt. So now as you see, when the value of zeta is small, almost close to 0, then you actually see a heavy oscillatory behavior. As you increase the value of zeta, meaning you go from undamped when omega is equal to 0 to critically damped, which is zeta equal to 1, then you're actually going to be eventually be damping very quickly. So your response is going to be dampened very, very quickly. So that's what you see. So that's 0.1, 0.2, and etc. So now really what you see here is just going to be the envelope of the response. So really this is going to be your so this is actually going to be your response envelope. So that's your envelope associated with zeta equal to 0.1. So now for zeta equal to, for example, 0.2, it's going to look, so your envelope is actually going to be looking like this. And that's going to be your envelope of the response. And you can actually, draw this envelope for even different values of zeta. So now let's talk about the specifications of the time response of second order system. So what you see here is the step response. So I'm just going to draw. So, okay, so it is actually a step response for particular value of zeta. So as you see here, there are actually few parameters defined. So what we call, or what we have here, is the so-called rise time, or TR, and then we have peak time, TP, and then we have settling time, TS, and we have what is called MP, or the first peak, which is actually this point right here, and we have the value of steady state, which I'm actually going to name it by YSS. So now some of these parameters you had already seen in the response of first order systems. For example, the rise time, we had defined it for first order systems, and we had also defined the settling time for first order system as well, and also the steady state value. But now there are a couple of new parameters, namely the peak time and the peak value, or the fixed, or the first and largest value of peak. And these are actually the couple of parameters that we did not have for first order system. Of course, the reason why we did not have them was that the step response of first order system did not really show any peak or any what we call overshoot. Okay, so now the rise time, the definition is going to be exactly as before. The time that takes for the response, for the step response to actually go from 10% of the steady state to 90% of steady state. And so this is still shown by TR. So the TS is actually going to be defined as the time that it takes for the system, for the step response of the system to just go to just to enter a region of 2% deviation from the steady state value, and it's actually going to stay and that in that region forever. So it's called TS, or settling time. And then we have a couple of parameters. Oh yeah, so we also have the steady state value. So that's going to be what is the final value of the time response after it gets settled down. Then we have two new parameters, TP and MP. So the TP, or peak time, is actually going to be the time in which the first and largest peak of the time response or the step response occurs. So for example, here you see that we have one peak here, we have one peak here, and there are also going to be perhaps additional peaks as well. But we are only going to be interested in the first peak. So the first peak or the largest peak, we show it by MP. And then so like I said, we define peak time and associate and the amplitude of the time response, or rather step response associated with that peak time, is called just peak value, or the first and the largest peak, MP. So I have already defined TR, the rise time, TP, the peak time, TS, the settling time. I also define for you the MP and YSS. But now, often instead of using MP and YSS by themselves, we actually use something else, which is called the percentage of overshoot. So the percentage of overshoot, if I go back one slide, so now if the response is supposed to eventually settle at the final value YSS, but it shows a peak or an overshoot, and it actually goes as high as, let's say, MP. So this percentage of change beyond the steady state value compared to the steady state value, it's called a percentage of overshoot. So this equation just shows you that, so the difference between the peak time, the value of peak, and the steady state response divided by the steady state value, it's actually called the percentage of overshoot, or PO. Sometimes it's just shown by percentage OS. All right, so without going through the math or the proofs for this equation, I'm actually going to show you just the final equations. So the equation for peak time is going to be what you see here. So that's going to be pi divided by omega d. And if you remember, omega d was the damped natural frequency that was also defined as omega n square root of 1 minus zeta squared. So that's going to be your first equation. So TP is going to be pi divided by omega d. Then your next equation is going to be yes. So your next equation is actually the percentage of overshoot. So the percentage of overshoot is going to be what you see here. So you multiply e to the power of negative pi zeta divided by square root of 1 minus zeta squared by 100%. So as you see, the percentage of overshoot is only a function of zeta, which is a damping ratio. So if you know the percentage of overshoot, you would know the value of zeta. And if you would know the value of damping ratio, then you would know how much the percentage of overshoot would be. In fact, if you know the value of zeta from this equation, you can just plug in the value of zeta and get the percentage of overshoot. That's easy. But often you're given the percentage of overshoot, and you're asked to actually determine what the zeta is. And what you end up with is to solve a second order polynomial equation. And of course, you get two values for zeta. One of them is going to be positive, the other one is going to be negative. And so you're only going to choose the one that is going to be positive, and it's definitely going to be between 0 and 1. So, but again, it could be a difficult and time-consuming process to solve that second order polynomial to get zeta from percentage of overshoot. So instead of doing that, if I give you a question like this in the exam where I give you the percentage of overshoot and I ask you to find zeta, I'm also going to provide you with this plot. So this plot shows, or this figure shows the plot of percentage of overshoot as a function of zeta. So then if you know what is the percentage of overshoot, then you would have to find the associated value of damping ratio from this graph. So the next equation would be settling time. So equation for settling time is just 4 divided by zeta omega n. So that's something we're also going to use. So evaluation of TR is going to be a little tricky. So there's really no explicit form equation, no explicit equation that relates zeta to, that relates rise time TR to zeta and omega n. Instead, sometimes you're just given this plot. So this plot is actually a plot of omega n multiplied by TR as a function of zeta. So, so if you're given the value of TR, then then the value of TR is just going to impose certain points on this line. So, and if you also know the relationship between zeta and omega n, you should be able to just identify where you are on that line, and from that you can actually go ahead and calculate other parameters, other important parameters. So now recall that if the second order system transfer function is in the standard form of omega n squared divided by s squared plus 2 zeta omega n s plus omega n squared, we had actually shown that the two poles when zeta is between 0 and 1, so for underdamped case, the two poles would be negative zeta omega n plus minus j omega d. And again, the omega d is the damped natural frequency. So why is it important? So you're actually going to see it in the next slide. So in this slide, you see the location of the poles of second order undamped, underdamped system in S-plane. So now we actually have two poles, 1, 2, and the poles are complex conjugate. As I said, the two poles are located at negative zeta omega n plus minus j omega d. And in fact, this is negative zeta omega n, so the real part of the two poles is the same, and the imaginary part for one is j omega d, the other one is negative j omega d. So these are actually the two poles. So now really from here to here, that's going to be, so from here to here, that is going to be zeta omega n. From here to here, it's going to be omega d. Okay, so now we actually have, so this much is omega d, from here to here is zeta omega n. And turns out that this angle, so this angle that you see here, if you showed by theta, cosine of this angle is going to be equal to the damping ratio zeta. So really you can establish a few things. One is that if you know the location of the poles, from that you can actually find out a lot of things, omega n, omega d, zeta, etc. And if you know the zeta omega n, and you can easily determine the location of the poles on S-plane.